Have you ever noticed how your camera flash charges for a few seconds and then, boom, a sudden burst of light? That's a capacitor at work. Hi everyone. In today's session, we are going to explore one of the most useful electrical devices in modern electronics, the capacitor. A capacitor is an electrical component that stores energy, not as chemical energy like a battery, but as electric potential energy in an electric field. It's made of two conductive plates separated by an insulator called a dielectric. Now, when you apply a voltage across these plates, one plate builds up positive charge and the other collects negative charge. No current flows directly between them, but the capacitor holds that electric tension. We define the capacitance of a capacitor as the amount of charge it can store per unit voltage. So, the formula is capacitance equals charge divided by voltage. In other words, C equals Q over V. Where C is capacitance in farads, Q is charge in coulombs, and V is the voltage in volts. Remember, the higher the capacitance, the more charge a capacitor can store for the same voltage.
Let's now focus on the simplest type of capacitor, the parallel plate capacitor. Imagine two large flat metal plates placed parallel to each other and separated by a small distance. These are connected to a battery. When the battery is turned on, positive charge accumulates on one plate and negative charge on the other. This sets up a uniform electric field between the plates. The lines of force go straight from the positive to the negative plate. Now, between the plates, we usually insert a material that doesn't conduct, like air or glass. This material is called a dielectric. This setup, two plates, a small gap, and an insulating medium, forms the basic design of a capacitor used in everything from radios to microwave ovens to camera flashes. And remember, the smaller the gap and the larger the plate area, the better the capacitor.
Alright, time for some math. Let's derive the formula for the capacitance of a parallel plate capacitor. We start with our basic definition, capacitance equals charge divided by voltage, or C equals Q over V. Now, to find voltage, we recall that the electric field between the plates is uniform. It's given by electric field E equals charge Q divided by epsilon naught times area A, that is, E equals Q over epsilon naught A, where epsilon naught is the permittivity of free space. Now, the voltage between the plates is just voltage equals electric field multiplied by distance, that's V equals E times D. So substituting for E, we get V equals Q times D over epsilon naught A. Now plug this into our formula for capacitance, C equals Q over V, which becomes C equals Q divided by open bracket Q times D over epsilon naught A close bracket. The Q terms cancel and we are left with capacitance equals epsilon naught times area divided by distance.
What happens when we insert a dielectric between the plates? Well, a dielectric is an insulating material, like glass, mica, or plastic, that changes how the electric field behaves. It reduces the field inside the capacitor, allowing more charge to be stored for the same applied voltage. To quantify this, we define a term called the dielectric constant, symbol K, which is always greater than 1. With a dielectric inserted, the new capacitance becomes capacitance equals K times epsilon naught times A divided by D, that is C equals K epsilon naught A over D. This means the dielectric multiplies the capacitance by K. For example, if you insert mica with a dielectric constant of 6, the capacitance becomes 6 times larger. This is exactly how we design compact high-capacitance capacitors used in electronics today, by choosing materials with large dielectric constants.
So what happens to all the charge a capacitor stores? Well, it stores energy in the electric field between the plates. This energy comes from the work done in moving charges onto the plates. The energy stored in a capacitor is given by U equals 1/2 CV squared, which means energy equals 1/2 times capacitance times voltage squared. Alternatively, you can write it as U equals Q squared over to C, or U equals 1/2 Q times V. All three are equivalent, just different versions depending on what you know. So, for example, in a camera flash, the capacitor charges slowly over a few seconds, then releases all that energy at once to power the flash. If you were to plot energy versus voltage, you'd get a parabola, meaning the energy increases rapidly with voltage. Let's now solve an advanced example using these concepts. A parallel plate capacitor has plates of area 0.02 square meters separated by 2 millimeters. It's filled with a dielectric of constant 5. It's connected to a 200-volt supply. We need to find two things. First, the capacitance. Second, the energy stored. Step 1. Calculate the capacitance using the formula C equals K times epsilon naught times A divided by D. Substitute the values. K is 5, epsilon naught is 8.85 into 10 to the power minus 12, A is 0.02, and D is 2 millimeters, which is 2 into 10 to the power minus 3. Multiplying it out, C equals 5 times 8.85 times 10 to the power minus 12 times 0.02 divided by 2 times 10 to the power minus 3. The answer is approximately 4.425 times 10 to the power minus 10 farads. Now for step 2, calculate energy stored using U equals 1/2 CV squared. So, U equals 0.5 times 4.425 times 10 to the power minus 10 times 200 squared. That gives us energy equals approximately 8.85 microjoules. So the capacitor stores just under 9 microjoules, enough for a quick discharge.
Let's take a moment to wrap everything up. We learned that a capacitor is a charge storage device, and that the simplest form is the parallel plate capacitor made of two plates separated by a dielectric. We derived its capacitance using C equals epsilon naught A over D. We saw how inserting a dielectric increases capacitance by a factor of K, giving us C equals K times epsilon naught A over D. Then we discussed how the energy stored in a capacitor is calculated using U equals 1/2 CV squared. Finally, we tackled a numerical example that brought together area, plate separation, dielectric constant, and voltage to compute both capacitance and energy stored. Capacitors are more than just theoretical tools. They're inside your phones, laptops, power systems, and even your electric toothbrush. I hope this session helped you understand how capacitors store energy and how their design influences performance. In the next session, we'll take it further and study how capacitors behave in series and parallel combinations. Till then, keep questioning, keep calculating, and keep enjoying physics.